So, hello all, welcome to my thesis defense. The title of my thesis is Cloud MEMS as a cloud-based lightweight solution for MEMS design and simulation. And then there is a extended part of it which says aim to improve accessibility, performance and collaboration during all stages of MEMS modeling. I'd like to thank all my committee members for supporting me and for being here today. Let's go with the outline. So this is how I will be going through the whole presentation. There will be a little bit of introduction where I'll be introducing MEMS and talking about simulations also. Then we try to look at the motivation of why we would use cloud MEMS or why we came up with the architecture idea. And then we'll talk about how the architecture was built and then what was the simulation software choice that we had performing a simulation in cloud MEMS, overview of all the components in the architecture. There is a concept of geometry templatization which we have introduced in cloud MEMS. That is also something which I would put some focus on. Then we'll look at how cloud MEMS works on the cloud, some use cases, conclusion, and some future work. Then acknowledgements followed by a very little demo. So to start with, what are MEMS? MEMS are micro electromechanical systems. These are very tiny devices which are used as sensors and actuators. And these contain both mechanical and electrical components. Okay? So majorly used for sensing and actuation. These are two simple examples. And since they are sensitive to heat and vibration and other environmental conditions also, it is imperative that we understand their behavior under these conditions before using them for sensors. And that is where simulation comes into picture. So in order to understand their behavior, we can either try and fabricate them all the time and then check the behavior, modify it a little, check the behavior. That would be extremely costly. The better way is to just use computer-based simulations with a certain threshold of error and then find out what your required device design is. Now let's look at some of the advantages of simulation-based modeling. There is an example shown there on the right-hand side, which is from a famous simulation software. It's called Console Multiphysics. And what simulation modeling does is it helps us understand the behavior of the device under many circumstances or many situations. And then it makes it less expensive and it is less time consuming. I'm sorry, that part is hidden a little. It's less time consuming because you don't have to make the actual device, you just do it on the computer and you can quickly understand the behavior. And it also allows the concepts and ideas to be verified, communicated and understood, because you would be having 3D models, 2D models, you can rotate them, you can look at the results at any level of depth that you require. Now, these kind of simulations require very sophisticated CAD suits. So the simulation method which we are talking about here is called finite element analysis simulation. What it does is it takes a big geometry and it divides it into several small components to calculate solution on each component and then merges the solution into one big complete solution. But finite element analysis, the focus that I'm trying to shed some light on is that finite element analysis method takes a lot of memory, because that whole division process, there is something called as meshing in that, it all takes a lot of time and a lot of processing. So that's why those sophisticated CAD suits have enhanced modeling capabilities which are given in them. Now, of course, if they are sophisticated, they have a lot of advantages and disadvantages also. But we are going to consider them challenges because those are the challenges which we are going to try to resolve here. So, the advantages of those suits are that their processes are highly optimized because they want to solve for huge computations. So they have gone through a lot of optimization and their solutions are reliable. But there are certain challenges that we face with them. One is that they require a very powerful infrastructure to install, okay, because otherwise a simulation could take over days, and that would be not very helpful. Then, since they come out with a lot of features, that's why in order to learn all those features, in order to learn the whole flow of simulation, or in order to learn how to use those softwares, the learning curve is very steep, and ultimately it takes a lot of time. That is why I said it's time consuming also. Then, since they are providing so many features, the license cost also goes up a lot. So let's see if we can tackle all these challenges and still give a simulation capability to people. A plausible solution which we came up with could be a web-based interface for visualizing everything. By that I just mean that there is a website which you open in your browser, and you should be able to see all your simulation results, perform simulations from there without having to install or buy any huge infrastructure. Now, of course, for this kind of visualization, there is a lot of data that would be transferred from somewhere, so that data needs to be stored somewhere. That data is usually stored in text and file formats in our case, okay? We have talked about visualization, we have talked about storing data, but where is the simulation capability? The simulation capability can come from writing our own simulation engine. The problem is that would be like reinventing the wheel when there are already so many simulation engines available. So best is to provide an asynchronous integration with the CAD product, which has simulation capabilities. But the question is that we don't want users to have to install those CAD products anywhere. So where would the CAD products even reside? The CAD products can reside on cloud, or cloud computing offers infrastructure as a service where you can just deploy it on the server and users just open the website and perform simulations. Now, how would such an architecture work? So from this slide, the takeaway is these two things, and of course, the question on simulation capability. Let's try to build the architecture now. So we started with a website and a storage capability. The next part is, how do these two connect? Okay. These two connect using something called as REST services, or using a controller which is going to control the flow of data between this and this. Okay. So of course, this is also going to reside on a server, and this is also going to reside on a server. This is something which will be opened up on everybody's client, everybody's machine. In fact, this kind of architecture does have a name. It's called Model View Controller Architecture with SOA. Model View Controller Architecture is referred to as the storage model which you have. View refers to what you would be showing to the user, and controller, as I've said before, is something which controls the flow between the view and the model. And there's something which we have implemented. I'll talk about the advantages of this later on in future work. It's called SOA. It's also called Service-Oriented Architecture. So what we are trying to do is we are making sure that although this thing controls the flow between these two, but it is also loosely coupled with these two. So we can switch this thing out and put something else in, or we can switch this thing out and put something else in. Okay, this is what SOA enables. Now, we talked about a visualization mechanism, a website, a transferring and everything, but we never talked about the CAD engine. So where would the CAD engine go? Let's see, we have various options where we can combine the CAD engine. The first option is, let's try to combine it with the web client. We also stated that we don't want users to have to install this, so this thing goes out of the window. Then the next capability is that we try to merge this into the services layer. What's going to happen in that case? I told you a simulation can take up to hours or even days. So what's going to happen? You try to click simulate here, it's going to go to the services, and since this is integrated within the services, your whole website will be hung up till the simulation is completed. So this method is also not recommended. The third and the only method is that we use the file storage and make an asynchronous form of integration with the CAD engine and the file storage of the database. So this is the architecture that we decided to go with. What's going to happen in this case is that the website will keep functioning always, and as and when a simulation job comes into the database, the CAD engine is continuously going to keep looking for the simulation jobs. As it finds one job, it's going to get all the parameters for the job asynchronously from the database and the file store, execute it, put the outputs back into the file store, and this flow again will be able to show you the outputs which are placed by the CAD engine. So that is the asynchronous integration.
So CAD engine is not stored on the server?
No, that is also stored on the cloud server. This was only to show the MVC architecture, not the server client. So the things which are stored on the server are services, this data store, and the CAD engine. Okay? So users will just have to interact with the website, as I said here. Now, in order for all these connections to work, there are different kind of protocols already defined. I mean, we did not have to define anything new. The protocols are usually called JSON and FTP. So JSON is a protocol which is used to transfer text data to the server from the client, and then FTP is something which is used to upload files from the client to the server. Similarly here, and for accessing the website, the protocol is HTTP or HTTPS. We ended up using the secured protocol, that's why we are using HTTPS. Okay. I just tried to build the architecture in front of you all. Now let's look at the real architecture. This is the real architecture. If you look at it, it has the same blocks. There are just names given to those blocks. One is Cloud MEMS client, Cloud MEMS services. There is a Cloud MEMS storage layer, and then there is a Cloud MEMS engine. Okay. So it's the same architecture. This part is MVC, and this is the integration layer. And now the only difference here is that we have defined the CAD engine that we have used. We ended up integrating with console here. Okay. Now the question is, why would we choose console? There are several reasons for choosing console. The first is, so if we want to interact with the CAD engine, we need to make sure that we can programmatically connect to it. We don't want a guy sitting there conducting simulations based on whatever simulation jobs are there. So we wanted to automate the simulation process. That's why we needed an API for simulations. And console comes with a published Java API for importing geometries, conducting a simulation, and then exporting the plot data. Consider console as a black box, which is going to take all the inputs from you and give out all the simulation outputs, which you can then show to the user in the plots. Now another part of console is that it allows client-server communication with console server. Now that client-server communication enables you to conduct several simulations parallelly using one server. That is the normal client-server fundamentally. Then it supports multiple geometry formats. Now, of course, if we are trying to conduct simulations on a CAD geometry, we need a format which is suitable to the engine which we are using to display geometries and console. The common format which we found out was stereolithography, STL format. That is the format which we are using to transfer the files in. Then, console also gives a lot of physics module couplings for MEMS, because this is primarily devised for MEMS systems or MEMS simulations. We found out that console has an API and it gives a lot of MEMS simulations also. So console had a perfect potential to be integrated. Now, since we are using console, we need to understand how to perform a simulation in console, and that would also reflect partially how we would be performing simulation in Cloud MEMS. Now let's look at how do you perform a simulation. You select a geometry, select which simulation do you want to perform, and then provide the required boundary conditions. Now this is something which we'll go into the details in the upcoming slides. And then schedule a simulation, because there is an asynchronous asynchronous execution of the simulation schedule. Now before we go into the actual workflow of a simulation, let's look at some of the concepts which are required something like boundary conditions. So in order to understand boundary conditions, we need to understand if we are trying to simulate environmental conditions, how do we provide those environmental conditions in our software? There are many ways. You represent topology of a geometry as a point, surface, or volume selections. In the console terminology, these are called vertex, boundary, and domain selections. So if you're trying to select a volume in a geometry to allocate something to it, we'll see that in the next slide, it is called as a domain selection. If you're trying to allocate something to a surface, it's called as a boundary selection. I did talk about allocating, but I didn't mention what do we want to allocate there. So this shows some examples of allocating stuff. So boundary conditions are where we allocate physics or apply physics to those selections that we want to. In order to simulate an environment where we want to see how our device behaves. So for that, here is an example that shows a domain selection. What it shows is that polycrystalline silicon material has been allocated to domains 2 and 3 of a geometry. So if I go back to the previous slide, I can say that this is domain 2 and this is domain 3. They are made of polycrystalline silicon during the simulation. Similarly, I want to define some terminal boundary where I would be applying a potential of 1 volt. So I can just define that these boundaries 6, 7, and 9 will have a potential of 1 volt applied to them. During simulation, these will be considered, and finally the simulation will be performed accordingly. This is how you apply boundary conditions. Now, having seen all the concepts, let's look at the actual workflow of how do you perform simulations. As I said, 4 steps are involved. First is you import or create a geometry. After creating a geometry, we want to fetch all the topology for that geometry, and since console is the one conducting simulation, console has to be the one who fetches all the topology. So we commit a geometry for that. You commit a geometry, asynchronously console is going to give us the topology of that. If it is not successful, you go back and create another one. There can be several reasons, but if it is successful, you proceed to step 3, which is selecting a simulation, boundary conditions, and scheduling a simulation. Now we have introduced some validation checks for the simulation. If those validation checks passed, what you do is your simulation gets scheduled and the engine conducts a simulation. The simulation status changes. It's either failed, conduct another one, or if it's successful, go to step 4, which is view the results of a simulation. And that is where your workflow ends. 4 simple steps. In fact, 4th is also just viewing the results. So 3 steps to actually do work. Now, having seen the workflow, let's have an overview of the component applications in CloudMems. There are 3 applications as we discussed. The first is services. As I said before, it is just going to go on the data transfer between the client and the storage. Furthermore, in order to implement some level of security, it also maintains user sessions and validates their integrity in every request. Okay. Now, looking at the engine and the overview of the engine, it's a Java-based simple scheduler application. It integrates with console API, and we are providing 7 different types of simulations. Those are just examples that we have provided because we wanted to showcase the capability of doing simulations. Then, since this is the part which is actually doing the simulations, it is the most memory intensive and time consuming, and that is why it presents a performance enhancement potential also. So if you can buy a stronger cloud infrastructure, you would be able to conduct your simulations faster. Last part is CloudMems client. Looking at the overview, it's a lightweight user-facing web application or a lightweight CAD website. And it's built on a single page application concept. We did not want users to have to navigate between pages and then lose all context. So that's why we developed it as a product. And since it's lightweight, it does not perform any computations. All of them are performed on the server side. Then it uses Three.js for 3D rendering and REST services to retrieve and send the data. Okay, let's look at how the website looks like. So this is how the homepage of CloudMems looks like, and of course it is divided in 4 modules. The modular structure is only implemented because we wanted to make it an SPA, single page application. In case you have created your geometries outside of CloudMems and you want to use them to simulate here, use imported geometry. Just import the geometry here, open it and simulate. You want to look at all the results of the simulation, so you look at the viewer, which has 3D rendering capabilities. You want to look at your history of all the simulations which you have performed a month ago. You look at simulation results. You want to manipulate the data in CloudMems, perform new simulations, view the results which are clickable, downloadable. You do it here. And then there is a builder tab which allows you to create geometries. Let's be honest, 2 steps are involved. One is creating a geometry, second is simulating. Let's look at the geometry creation and templatization. This is pretty much the last part. Geometry creation can be done using simple shapes. You can create it with boxes, cylinders, and then there is something called as point-based shapes which we have given. But if you're having complicated geometries and you just want to move 1 parameter or 1 bar longer, if you just want to create 1 bar longer for the next simulation and you have to do that after a month, creating the same geometry again is going to be a pain. That is where we introduced a parameterized builder which allows you to define your own variables, define your own constraints for those variables, and define your own shapes which have parameters based out of expressions built on those variables, and ultimately you can share them with other users. This is how we enable CloudMems for expert and non-expert users. Now, we have seen how CloudMems works, we have seen what CloudMems is. Let's see how it works on the cloud. We did a simple POC deployment. There is a cloudmems.xyz domain which we have bought, and then this has been bought from Route 53. We devised an application load balancer from Amazon Web Services, and everything in the application is deployed on an EC2 instance. Furthermore, we are doing asynchronous simulations, so let's say your simulation completed overnight, you need to be informed about it. So we are sending emails to the users by using Amazon Simple Email Service. Let's look at some of the sample use cases. Now here I'm not trying to focus on the veracity of the MEMS device. I would just be focusing on creating geometry in our interface, being able to simulate it and being able to view the results. So this was a sample thermal actuator which we created. We fixed the top 2 ends, passed electric potential to one arm, made the other one as ground. These are the boundary conditions which you provide. Then chose polycrystalline silicon as the material, heat flux, defined the heat flux as a boundary condition. These are the plots that came out. As you can see, if you want to see the actuation, there is a deformation in the geometry here, and that is what can show you how the geometry behaves. These images have been taken from CloudMems. Looking at the last sample, which is a simple parallel plate capacitor which I created. So there is electric potential, ground, polycrystalline material, air, and simple plots for showing how the capacitance or electric potential was distributed throughout the geometry. So in conclusion, CloudMems enabled both expert and non-expert designers to create geometries with the use of Builder without installing any CAD system on their machine. Of course, that is why we reduced the cost of conducting a simulation. And we save time because you can keep scheduling simulations and leave for the day they'll be done the next time you come back. There is some future work in this. You can obviously add a lot of simulation types, and then this is a potential marketplace also, because if you create geometry templates which are parameterized, they can be sold to other people or they can be shared with other people at an expense, and this can become a marketplace. Of course, the architecture elasticity enables performance improvement whenever you get a better infrastructure. And as I said, we are using service-oriented architecture, so you can create new clients also for this. So you would be able to conduct simulations on tablets without making much changes in the whole application And for the acknowledgements, I'd like to thank Dr. Vijay for supporting me throughout the project, for motivating me, and for presenting me with several other opportunities. Dr. Gorgev for having all the technical discussions with me, and also being a moral support, and also giving timely feedback. Dr. Ledgard and Dr. Kaur for being here in my committee. Dr. Javed for having a discussion about security with me. That is why I implemented HTTPS. Mitch for bringing all the electrical engineering related expertise in that. I'm not an expert in MEMS. It was all due to the inputs from Mitch. I just worked on the computer science aspect of this project. Then Abhishek for helping me out throughout the thesis writing process. And Ayush, Osama, Parashar, Colin for answering all my questions during the thesis writing. The ECS department, everyone here, and my colleagues and my family. Thank you. And if anybody would like to see the demo,